First of all, let me say that it's a pleasure to be here on this remote session of FSEN. It's a pity that we are not able to be together in a room, but okay, it's what you can do nowadays. And let me congratulate to your organization, because the edition is being quite nice. And I will present this joint work with Mario Benevides from UFRJ Brazil, and with Manuel Martins here from University of Aveiro, in adding proof support to epistemic logics with structured knowledge. Okay, so let's say firstly that nowadays with this even pushed by the emergence of 5G and for all the new algorithms that you have, like the blockchain technologies and distributed ledger technologies that evolves this kind of multi-agents that have its local perceptions and shares and owns its own information and knowledge. There is actually a need to try to see and try to develop new techniques suitable to design and to verify such kinds of systems. And if you look for what you have today in the literature and in the logic, we have these really nice multi-agent epistemic logics that are not a new topic. It's a topic with some 2 or 3 decades. That are a kind of model logic, okay, that is dedicated to reason about systems with agents that have its own knowledge and beliefs, and it is already used, for instance, to verify some kind of simple communication protocols, and it have been used with success. But the point is that the way we represent knowledge on that logics are just by sets of propositions, okay? And obviously, whenever we want to apply such kinds of techniques to other scenarios that involves more data, that is not that with some levels of heterogeneity in really complex systems. This representation of knowledge as proposition is sometimes not rich enough, okay? And it would be nice if you could, or it's a need to try to develop other formalisms with richer features to structure and represent our knowledge. And how kind of structures? So if you look for what we have in computer science to represent information and data, we have all of these very well-known structures like algebras, graphs, even programs, whatever. All of these prove that are really nice and you know it very well. So the point is, why not consider other epistemic logics where on place to be states, epistemic states, just represented by sets of propositions, do not consider other more religious structure like one of these that we have here. And but by the way, our approach and it does not start it on this paper. We are already working from some years today to now with other model logics with the same lines. We will not introduce or will not try to define one logic, epistemic logic with which states are algebras and other which states are graphs and so, but we have a parametric method to construct such kind of logics. Okay, this is what we call by multi-agent epistemic logic with structured knowledge, and this was a work that is not started. Even now, I'm talking about epistemic logic, not starting this paper, but with 2 years ago, in a first version with some team in the LSFA conference. And what we will do today is extend this work, because this logic were just defined in a semantic point of view. Now I will introduce also parametric methods to provide logical calculus for these parametric constructions, okay? For all of these instantiations. And regarding to outline of our talk, Firstly, I will just make a brief presentations about this standard multi-agent epistemic logic, that is the basis of this work. Then in a second moment, I will introduce our method, this method of constructions of epistemic logic with structured knowledge states. And then we will discuss our contributions on generation of this proof calculus, and we will terminate with some notes. So, just in one slide, whenever you look for these works that from hands of Vitinka and a lot of other works, it is a very well-known formalism. Regarding to the signatures, there is the symbols that we need to express our formulas. We just need a set of propositions and a set of agents, okay, or agent symbols. And then, whenever we start with our formulas, these are just modologic formulas, okay? Here we have this modality K that is more or less the point here is that this formula will be true in epistemic states if the agent A knows that phi is true, okay? And then we have also this common knowledge modality. This common knowledge is just a subset of agents, and this will be true in a state where all the agents that belongs to G knows phi, and as well as that all the people or all the agents on this group knows that the other elements knows, and so on. This is a transitive reflexive closure pattern, okay? And moreover, I can also consider the other Boolean connectives by definition, like the implication, the junction, equivalence, and so. And we have also this other dual modality that is a kind of a diamond, if you consider the K as a box, which says that agent A believes that phi is true, okay? And then regarding to the models are just a special case of the Kripke frames. We have again a triple with states, and we have these accessible relations. That here, the difference is that for any agent, I have an equivalence relation, not just a simple relation as we have on standard model logic. And also the idea here is that this relation will provide us the epistemic perception of the agent A, and then we have also evaluation, which assigns propositions to sets of states. Okay, again, in order to interpret the common knowledge modality, firstly I have to consider this relation G, which makes the union of all the agents in G, and then we have the reflexive transitive closure over the G, okay? Then regarding to satisfaction, now this is defined exactly as we have on standard model logic. And again, here is the same, but this means that on state W, agent A knows phi if and only if for all the states that are epistemically indistinguishable with respect to agent A. On W, we have that phi is true on that W prime. Okay, and again, for the common knowledge, I just have to use this R's G star that I defined in the previous slide. Okay, just a simple example that we can find in the literature. This is a classic from the literature. Suppose that we have a game, we have 3 players, Anna, Bob, and Clara, and we have 3 cards that I will distribute it randomly by the 3 players. Each of these players only knows his own card, okay? And then, okay, we will use the propositions, for instance, 0A to say to denote that agent A or Anna has card 0, and for instance 2C to say that Clara has card 2, and then we will use also this propositional notation for states. Okay, whenever I have here 0, 1, 2 says or denotes the states where Anna have the card 0, Bob have card 2, and Clara have the card. Bob have card 1, and Clara have the card 2. And then using this, I can have this epistemic or this knowledge representation of this epistemic model of this game. Okay, look here on state 0, 1, 2 for the player Anna that have the card 0. she cannot distinguish this state to that state. Okay, for Anna, it's equivalent to state where Bob have the card 1 and the Bob have the card 2. And then we can, for instance, check that it is true on the states that Anna knows that Bob have the card 1 or the card 2. Moreover, if you look for this state here, 102, I can also see that the Clara believes that Anna have card 1 and Clara believes that Anna have card 0, because I can see on through the relation of Clara, I can goes from that state to that state, okay, and also for that state to that state. Note that, as I said, the accessible relations are equivalence relations, so they are reflexive. So for simplicity, we do not note the loops, but we have a loop in all of these states for the three agents, obviously. Okay. Then let's look for our method. Okay. The point is that I need, as I said, the idea is to plug a local model for each one of the states. Okay, I will have a layer in our framework that is that represents the structure of the standard epistemic logic, and then for each states I have plugged a model on the with that more richer structure like algebra, graph, or whatever. Okay, so I need also a local logic to represent these properties about such local states. Okay, and then for this reason I use this parametron method. That is a logic. I will call it here by the knowledge representation framework, but it's a tuple which have a set of formulae, okay, a set of models, also a satisfaction relation which assigns models to formulas, and an inference relation that is a syntactic calculus like an Hilbert calculus, if you want, or other kind of logical calculus, which assigns sets, which relates sets of formulas to formulas, okay? And as usual, we say that is highly sound if everything that I can prove on this syntactic calculus will be true in all the semantic structures of our knowledge framework. We say that this is complete if everything that is true on semantics I can have a proof on this inference relation, and also I said that this is decidable whenever I have a method or a procedure to decide if we have or not a proof for a given file, as usual. And then the idea is that I pick my layer and I have a kind of an asymmetric construction, a symmetric combination of these two logics. The logic that's the standard epistemic logic, and also the base knowledge representation framework that we adopt. Okay, so we just have to look again for standard epistemic logic and then make that exercise. Regarding to the signatures, for instance, on place to be here a set of propositions to represent this simple or this standard knowledge representation, I have a signature of the base logic. Okay, then on the formulas, I have exactly the same, but on place to be here propositions as atoms, I have here this the formulas over the base logic, okay, on this L. And then the states, the models are defined on the W as usual, a set of states. We have again a family of equivalence relations, exactly as we have on standard case. But here on place to be evaluation, which assigns propositions to states, what I have is a function which assigns for each states a model on the local logic. Okay, that's just this what we have. Some examples. Okay, regarding to the satisfaction, I define everything as usual, but here from the base case we say that this phi zero is a formula on the base logic. Okay, is true on W if and only if phi zero is true with respect to the satisfaction relation of our base knowledge framework on the model that is plugged to W. Okay. Some examples. Let me try to the propositional epistemic logic, the case that captures the standard case. If I want to capture the standard case, I just have to consider propositional logic as base and then build that construction over it. And in fact, the unique thing that is clear, that is the same, this is exactly the same, but with the change just the form. We have for as a base model, what we have is a function. Okay, we just assign the propositions to true or false depending on its value on the state W. Okay, this is just this is discussed on the paper, just instantiation and the revisiting of such example. Now let's see other different examples. Suppose now that we want an epistemic knowledge which knowledge are represented as graphs. Okay, so a good choice to do that is using, for instance, an hybrid logic with binders. Okay, that is a formula that is well known and that is really nice to represent graphs. As an illustration, let us consider now this game. I have these 4 graphs, okay? And now we have 2 players, Anna and Bob, that know something about the graphs. And then they will try to discover what is the selected graph that is not, that they didn't know. And for instance, Anna knows that the graph is deterministic. Okay, so on the eyes of the agent Anna, the graph could be this one or that one, okay, or that one. This one, no, because, no, sorry, the first one and third one, okay? This is not deterministic, obviously. And Bob knows that the graph has exactly 3 states. So on the eyes of Bob, it should be this graph or that graph. Well, let us try to represent this using our framework, okay? So Anna, I can represent the determinism using these binder logics, for instance, which says that from initial state, if I want X, then I transit for another state and I bind this variable Y, and I know that all whenever I'm in state X, that was the first state that I bind, all the transitions goes to choose Y. Okay, this will be only true on states that are deterministic. So Anna knows that they cannot distinguish these 2 states, and these 2 states not, but they can distinguish first and second layer. Regarding to the Bob, that the graph has exactly 3 states, he considered 3 nominals, okay, and he knows that whenever I am, the state is marked by a binder, okay, and also the binders are different, so we have 3 states. And we can express other things more interesting, like Anna knows that Bob does not know that the graph is deterministic, using sentence like that one. Other examples, if you want to represent knowledge as algebras, okay, so we take as the basic knowledge framework the equational logic, okay, and then you can illustrate it with an example like this. So now we have these 4 algebras, okay, here is the integral algebras with usual sum and also with inverse of sum like the minus. Here we have the cyclic group with 2 points. Okay, and here we have again the integrals with multiplication, and we have here this 4th algebra with this strange binary operation, and then Anna knows that this binary operation that is representing this plus and these stars is associative. Bob knows that E is a natural element, and so we can express everything here just using equation as you did on equational logic, and you can deal with such kind of scenarios. Obviously, we can enrich. You can extend this framework, for instance, with public announcements. Okay, now we can consider, for instance, this new pattern of formulas. That is this is the I announce phi, then psi will be true, which will that we will reconfigure the epistemic model by assuming that in fact phi is true. Okay, for instance, on this, if you become to the previous example, and then if you announce that we can always make 2 transitions from the initial state, then obviously we can discard these two models and we can simplify our models just to that one. Okay, and we can use it to deal with a lot of other cases. Okay, this is just an example that we discussed on the paper. But now what we did on this paper, we continue that exercise, then trying to provide the proof support, okay, for that logics. Okay, and you remember that on the knowledge on our parameter on the knowledge framework we have two relations. First one for the satisfaction relation that I used on this semantical construction, and we have also this inference rule, this inference relation that we will use now. That, as I said, can be represented, for instance, as an Hilbert calculus. And then the principle of the approach is exactly to the one that I already mentioned. I will build epistemic dynamic logicals over the calculus of L, over the base calculus offered by the inference rule for L. And the intuition is that when you look for this inference rule of L, of dynamic epistemic logic, the standard one, this comes from the Serra-Gerber. This is a case from this Serra-Gerber calculus for the propositional dynamic logic. We have as the axiom all the propositional tautologies, okay? Here, I will use the theorems of L to take that role. Let's see what will happen. And moreover, after that, I will characterize all things like soundness, completeness, decidability, even complexity, if you want, parametrically on the characterization of L, because the epistemic dynamic logic we know very well, and you know all of these properties. Now you just have to play with the properties that comes from the base knowledge framework. Okay, so how can we construct this Hilbert calculus for the L, the composed logic? Okay, firstly, we consider the instantiations with formula of all propositional tautologies, okay, and we consider that axioms. These are the axioms of epistemic dynamic logic, okay. We have things like the introspection, that if agent A knows phi, then she knows that she knows phi, and all of that stuff. This is the very well known, discussed on the literature about the properties that you want to have on to represent knowledge and beliefs. And then we just put this new case that is that we will consider as axioms all the theorems of our logic. I have here a typo here. It should be an EL, okay, for any EL phi 0 for any theorem on base logic. And then we have the modus ponens and also the generalization of the model logic. And then, taking this calculus, I can prove, and you prove it on the paper, that if L is sound, it would be strange if you consider a base logic that is not sound, but okay. If this is sound, then we have that this new logic is sound. Okay, that is, everything that I can prove in this calculus that I presented in the previous slide is semantically true. It's true in all the models of this epistemization. Moreover, if L is complete, then this method preserves completeness. Okay, now the new logic is complete, is also complete. And moreover, whenever L is decidable, whenever we have a procedure to decide if a formula is true or not, is a theorem or not in L, then we have also decidability of L. And this is why, because we have the finite finite model property on the epistemic dynamic logic. And then if we have a proof on the point, if this is decidable, I can compose both decidabilities. Okay, and this is what we have. Regarding to the conclusion, let me just put it in a big frame of the works of the team. But the previous, firstly, we did a long a long way research on hybridization of logics in these hybrid logics. Firstly, with making this for constructing the logic on semantic level, then generation of calculus, and also some level of proof support, integrating it with that, and then we did this first step on the, as I did of this work in 2018, that was continued this year on this talk or in this paper, and we have also, for instance, other structures, other more recent works, for instance, with the Hybrid Dynamic Logic Institution for Event Data-based systems that continue with this on-demand principle on basis. But we have also in the literature other asymmetric combination of logics, and it would be important to mention here the temporalization of fitting. That is, as far as I know, the seminal work on this line of research that would put to transform any logic in a temporal logic. Okay, what was done? So we introduced this parametric generation of proof calculi to parametrically build epistemic logic with structured states, and we characterize parametrically the soundness, completeness, and citability. So what we have, there is a lot of things to do. This is a work in its infancy. So on one hand, we want to look for some instantiation of that method, for instance, the epistemization of probabilistic logic, or for instance, the epistemization of differential dynamic logic, and try to look to it as a logic with its own rights by studying more properties about that, by applying it to some case studies and so. And also, I'd like to work on the implementation of dedicated proof tools. I guess that we have here the receipt to do that. For instance, if you use some framework like Coq or Isabel, it would be nice. And but even taking into account this parametric nature of the methods.